Hello, dear students. Welcome to the channel and welcome back to the playlist in which we are discussing about different type of faults which can occur on power system in symmetrical faults and unsymmetrical faults. So we have seen different type of symmetrical faults. We have seen different type of unsymmetrical faults, and we have also seen symmetrical components in detail. We have covered pretty much every basic type of faults till now, and today I'm not going to discuss any theory or any concept. I just want to discuss some of the numericals from exam point of view, which will be, I think, important for your exams. So, before we start, please know that in order to understand this video, you need to go through all the videos of this playlist, and that is the major reason why I am putting this video in the on the last number of this playlist. So this will be the last video of this playlist, and if you haven't checked out previous videos in which we have discussed about the symmetrical faults, unsymmetrical faults, and different type of symmetrical components like positive, negative, and zero symmetrical components, so please check out the playlist. The link will be flashing on the top right hand side corner of your screen in the I button, so you can click on it and check out the playlist. And once you have checked out the whole playlist, all the videos, then only I recommend you to watch this video for better understanding. But if you already have knowledge about different type of symmetrical components, symmetrical faults and unsymmetrical faults, then you can go ahead and enjoy the video. All right. So now that's out of the line. Let's begin with some of the numericals with of symmetrical components. So let's start with this one. So the question says that one conductor of a three-phase line is open. The conductor flowing through delta connected load through line A is 10 amperes. So you have value of current flowing in one of the lines, it is 10 ampere, and with the current in the line A as the reference, and assuming that line C is open, we have to find the symmetrical components of this line current, right? So what is given in your data in the question, you have 10 ampere current flowing through A phase is available. We have to find the symmetrical components, so we have to find ia0, ia1, and ia2. Now for that we will need values of all three current flowing through all three phases, which means ia, ib, and ic, and then only we can find out based on the formula of three phase component, the matrix one. So we have to find the values of ic and ib as well. We know the value of ia. Now they have said IC conductor is open, which means if my IC conductor is open, then there will be no flow of current in C. So IC will be 0. And based on the KCL, because this is delta, and in delta, when you apply KCL, you can say that IA plus IB plus IC will be equals to 0. Which means if IA is 10, that means IB must be minus 10. So now you have values of IA, IB, and IC. Now you just have to substitute these values in the symmetrical component matrix. So remember what was the formula for symmetrical component matrix? So the formula was IA0, IA1, IA2 will be equal to 1/3 matrix A into matrix I, and matrix A stands for this, matrix A inverse, sorry, no, not A inverse. So A inverse stands for this: 1 1 1 1 1 alpha alpha square 1 alpha square alpha. Now remember, I've told you that this alpha stands for alpha is a complex variable, and it represents the magnitude and the phase difference between two phases. So alpha is 120 degrees, and alpha square is 240 degrees or minus 120 degrees. So we can represent it in polar form as well, and we also know what are the values of IA, IB, and IC. So let's substitute it. You will get instead of alpha you can write 1 alpha 1 angle 120, and instead of alpha square you can write 1 angle 1 minus 120 or 1 angle 240. And instead of IA, IB, IC, you know what is the value of IA is 10, IB is minus 10, and IC is 0. So when you now you have all the values, you can simply find the values of IA1, IA2, and IA0, and based on that you will find the value of IA0 is equals to 0. Basically take the you will take the multiplication of IA plus IB plus IC. IA is 10, IB is minus 10, IC is 0, so 0 10 minus 10 will be 0. Now for IA1, which is 1/3, 1 into IA plus alpha into IB plus alpha square into IC, right? So you know what is the value of IA. IA is 10 minus 10 into 1 angle 120. Value of IB is minus 10, so that's why we are having minus 10, and value of alpha is 1 angle 120, so we are simply multiplying it that with with this one. Now what we will do, we can convert this polar form equation into a rectangular form, and when we convert it, what you will get minus 5 plus j 8.66, and after doing that you can simply add the real and imaginary values. There are no other imaginary values except for j 8.66, so you will keep it as it is, and you will add 5 into 10, because 10 minus minus 5, so it will be 1/3 15 plus j into 8.66, and based on that the angle you will find will be minus 30 degree, and the magnitude will be 5.67. We are simply converted the rectangular form to polar form again. Same way you can find the value of IA2 as well, and when you do that you will find out that value of IA2 is same as value of IA1, so you can calculate that as well. Simply the angle will be inversed, right? The angle will be opposite. Now let's see this third one. This one is for the voltage. So it says the voltage across a three-phase unbalanced load are VA equal to 240 degree angle, VB is equal to 320 at 90 degree angle, and VC is equal to 480 at 340 degree angle. And we have to determine the symmetrical components of voltage this time. And they have also given the phase sequence, which is ABC basically. So we can simply directly implement the formula of my voltages, formula of symmetrical components of my voltages. So symmetrical symmetrical component matrix of V will be equal to 1/3 A inverse into matrix V. And matrix V is basically the voltages across my three phases. So again the value of alpha you know already, so I'm not mentioning it again. You have values of VA, VB, and VC, all three of them, so I'm not mentioning it as well. Now what you have to do, you simply have to take the multiplication, and you can find the value of VA0, VA1, and VA2. So when you do the matrix multiplication, what you will find? You will find VA0 will be equal to 200 angle 40 plus 320 angle 90 plus 480 angle 340. And when you convert, when you add all those values, because angles are different, so you have to convert this polar form into rectangular form, and then you have to add it. So when you do it, you will find your answer will be 1/3 604.2 plus 284.4J. And when you convert it into the polar form, you will find your voltage will be 225.6 volt at 25.2 degree angle. Same thing you have to do for VA as well. And whenever you do multiplication and then you convert that polar form to rectangular, then you will add it, and once you after adding that value, you will again convert that value, that rectangular form, into polar form. It's not actually necessary though. If you want to keep it that way, you can keep it that way as well. So if you want to state that Va1 is equals to 1/3 minus 491.6 minus J339.9 volt, then that is true as well. But actually the polar form gives us better idea about magnitude and phase, and that's why we use it. So to get a better idea of magnitude and phase, we will be converting the rectangular form into polar form. So when we convert again this rectangular form into polar form, the Va1 will be 199.2 at minus 145.3 degree. That will be the voltage of Va1, which is positive sequence voltages. Va0 was zeroth sequence voltages. Now for negative sequence voltages, right? For negative sequence voltages, again you will do the matrix multiplication, right? Simply you will be adding the matrices, and when you do it, uh, you will again find out that all the values of angle are different. So you will again convert it into the rectangular form. Either ways, if you don't want to change it, if you want to keep it that way, and if you want to do the um, addition subtraction operation even in the polar form, you can do it. But sometimes it is easier to do it after converting it into the rectangular form, so we have done that. So you will convert it into the rectangular form, then you will calculate its values, and again you will convert it into polar form, and Va2 or negative sequence voltages will be 187.12 voltage at 51.82 volts, 51.82 degrees. Now the final sum of symmetrical component series. After that we will be going through a different kind of sums. So this final sum says we have to find the symmetrical current components. So they have given the line current in ampere in phase ABC respectively. This time we are having our values in the rectangular form. So 500 plus j into 150, 100 plus j into 600, and minus 300 plus j into 600. And we have been asked to determine the symmetrical components of my current. So this time what we will do, we will simply again use that same formula which we used earlier in earlier two sums, right? Current matrix, the symmetrical current component matrix will be equal to 1/3 A inverse into the current vector or current matrix. And by doing that, you already know what are the values of Ia, Ib, and Ic. You know what are the values for what are the values of my alpha and alpha square. So what you can do, you can simply take the substitute those values in the formula, and you can take the matrix multiplication. Here they have converted that rectangular values into polar values, but it is okay even if you don't want to convert these rectangular values into polar values and directly want to do it, then it would be actually smoother operation, because to convert all these values into polar values is more difficult. So rather what you can do, you can simply convert the value of alpha into rectangular form, and then you can take the matrix multiplication, and then you can finalize it. That way it would be much easier, right? Because one is going to be 1, right? 1 plus 0 j. So you can simply convert one angle 120 degree and one angle minus 120 degree into polar form, into rectangular form, and you can simply find the multiplication of both of them. They have done the reverse thing, no issue, you can do that too. But whenever you find the final value of zeroth current component, it will be 1/3 300 plus j into 150. There is nothing new in here, so I'm not explaining the matrix multiplication and the step further after it. So I'm only discussing the final values. So final current value will be final zeroth current vector value will be zeroth current component value will be Ia0 equals to 1/3 300 plus j into 150, which will be 118.8 amperes at 26.56 degrees. Same way as you will be calculating IA1, and when you do so you will find out that value of IA1 will be one third, 1661.19 plus 13.03 J. And when you convert this rectangular form into your polar form, you will find the magnitude of current will be 553.73 amperes with angle of 4.34 degrees. Same ways you can calculate for IA2 as well, the negative component, and when you do so you will find out the rectangular form value of negative sequence current will be one third minus 438.81 minus 195.69 J. And when you take uh, the polar form of this rectangular form, what you will get: minus 160.15 at an angle 155.96 degree amperes. So now you have all three current components. Now let's see another sum. Let's see this one, right? And this one is going to be a little different from earlier sums. So again, read the question. What does it has to tell us? It says a 25 MVA 11 kV generator has XD at XD is equals to zero point 0.2 per unit, X2 is equals to zero point 0.3 per unit, and X0 is equals to zero point 0.1 per unit. Neutral of the generator is solidly grounded, and we have to determine the subtransient current in the generator and the line to line voltages for subtransient conditions when my YBG fault occurs at the generator terminals, and we have to assume pre-fault current and fault resistance to be zero. So always remember, whenever you are asked to find the value of subtransient conditions, line voltages or line current at subtransient conditions, when your YGB fault occurs at the generator terminals, what you will do first, you have to calculate the missing current components, uh, and then you have to find the value of voltage components, and based on that you can find the fault current and the fault voltages as well. So let's begin with my positive sequence current, right? So you know the formula already. Current will be equals to generated EMF divided by whatever my impedance is. Now we are not having Z1, Z0, Z2 because we are assuming pre-fault voltages 1 volt per unit at angle 0 degrees. So uh, whenever you are having whenever you are not having any angle, whenever you are having 0 degrees angle, you will only consider your reactance, and you are given the value of reactance, so you simply have to substitute it. Now you have taken assumed the pre-fault voltage 1 angle 0, so instead of EA you will write 1 angle 0, and you know the value of subtransient reactance, not transient, so it is zero point 0.2, right? 0.2 J to be precise, because we are taking reactances only, so it will be zero point 0.2 J. Then you know what is the value of X2, right? So you know the values of transient and steady state reactance 0.3 and 0.1. So you will simply substitute it, J into 0.3 into J into 0.1 divided by J into 0.3 plus J 0.1. Remember the formulas we discussed in the 6th chapter earlier, in the first or second lecture, I don't remember precisely, but we discussed this formula, and based on that you will be finding the pre-fault current. So when you calculate it, you will find out the pre-fault current is minus J 3.636 amperes. Now as I've said, we will be calculating for the voltages. Now we know that whenever my double line to ground fault occurs, the voltage the sequence voltages will remain equal, right? So my va1, va2 and va0, all three sequences will be equal. So if I calculate one, I will be calculating all three of them. So let's calculate for either one of them. You can call it ea1 sorry va1, va2 or va0, whatever you want to call it. And the formula will be same, based on, remember, when we draw the equivalent circuit for this condition, LLG faults, va1 was equals to ea minus ia1 into xd double dash. You already know the value of ea1, you already are aware of value of xd double dash, and you just calculated value of ia1. So you can simply find the value of va1, and the value of va2 and va0 will be same as va1. So no questions there. Now that you have values of all three of them, what you can do is you can calculate the current based on this. Now you have va1, you have all three symmetrical component voltages, so you have to find the symmetrical current components, right? So va2 will be equals to minus va2 divided sorry ia2 will be equal to minus va2 divided by x2 from the formula we earlier derived. You know the value of x2, you know the value of va2, so you can find value of ia2 will be equal to 0.909 j. Same way as you can find the value of ia0 minus va0 divided by x0, and its value will be, because you know both the values va0 and x0, so the value of ia0 will be 2.727 j. Now remember, in double line to ground fault, what was the case? The addition of two line currents was equal to the third line current. So in the symmetrical component only, okay, so ia2 and ia0, the addition of ia2 and ia0 will be equal to minus ia1. So we will simply add ia2 and ia0, and we will calculate the value of minus ia1, or rather you want to call it ia1, you can call it ia1. So just to verify the value of ia1, and when you do so, you will find the value of ia minus ia1 equals to j 3.636, and you will again verify with the value we derived earlier. Here ia1 is equals to minus j 3.636. If that matches, you are on a correct path. Now you simply have to calculate the fault current and fault voltages. So it is very basic, you know the formula. We simply, the fault current ib plus ic is equals to 3 into ia0. You know the value of ia0, so you just multiply it with 3 and you will find the value of fault current. So it will be j into 8.181 per unit, and then you will find the actual fault current. So you know what is the formula for actual fault current as well, right? You will simply take the fault current, and after that you will take the multiplication of it with your MVA, and you divide it with 3 into V, right? And when you do that, whenever you calculate fault current into MVA divided by root 3V, you know the value of fault current you just derived, you know the MVA value, it is given in the question itself, root 3 into, you know the value of kilowatt, kV, 11 into 10 raised to 3, it is also given in the question. So whenever you do the math, you will find out the value of actual fault current, which will be equal to 10.734 kiloamperes. Now for the voltages, VA, VB and VC, and after that VAB, VBC and VAC. So VA is basically sum of all three symmetrical components, and remember all three symmetrical components hold the same value, so you can just simply take the same component 3 times, so 3 into VA1, and when you do so, you can find the value of VA, which will be 0.8181 per unit. VB and VC, because both of them got short circuited and then at the same time grounded, VB and VC will be 0. And because this is my LLG fault, okay, so VB and VC will be 0. And now for the line to line fault voltages, what you can do, you can simply take the value of your voltage and you can multiply it with total voltage divided by root 3, right? So VA will be 0.8181, we just calculated it here, into 11, which is the kV given in the earlier generator, kilowatt given in the question earlier, divided by root 3. So when doing math, you will find out the value of VAB will be equal to 5.196 kilowatt. Same way you can find the value of AC as well. You know the value of AC will be again equal to V8 is equals to 0.8181, same value as my VA, into 11 divided by root 3, and my value of my VAC will be 5.196 kilowatt. Although when you find the value of VB, it will be 0, right? Because you're having LLG fault. Now let's move to another question. This question is again different, little bit different from earlier question. They have asked that an unloaded star connected solidly grounded 10 MVA 11 kV generator has positive, negative and zero sequence impedance as 1.3 ohms, zero point 0.8 ohms and 0.4 ohms. I'm not saying J values, I'm just saying imaginary values respectively. And single line to ground fault has occurred at the terminal of generator, and we have been asked to calculate the fault current. We've been asked to determine the value of the inductive reactance that must be inserted at the generator neutral to limit the fault current to 50% of value obtained, right? So what you already have, you have the value of base MVA 10 MVA they have given, you know the value of base kV, it is 11 kV, and you know the value of positive, negative and zero sequence, so zero sequence impedances, so you know the value of x1, x2 and x0, right? Now because we have been given base values, and considering these base values, we can calculate positive, negative and zero sequence reactance of my alternator. So you will simply can take x1 is equals to the positive sequence impedance into my MVA divided by my kV square, and you can find the per unit value of x1. Remember we earlier classes we saw how can we find per unit reactance. So we will calculate the per unit reactance for x1, x2 and x3, x1, x2 and x0, which is given as x into MVA divided by kV square. So we will be finding x1 positive sequence 0.107 per unit, 0.107 J per unit. X2 will be the negative sequence 0.8 into 10 divided by 11 kV, so 11 square, and x2 will be 0.066 per unit. X0 will be same ways 0.4 into 10 divided by 11 square, which will be equals to 0.033 per unit. Now we have to find the value for the LG fault, the current for LG fault. So the fault current will be equals to 3 into IA1, which is my positive sequence current. And the formula for positive sequence current, if you remember from LG fault, is given as 3EA divided by x1 plus x2 plus x0. Now you already have values of x1, x2 and x0. You are assuming the value voltages as unity. So the IA1 will be 3 into EA will be 1 divided by 3 reactances and the final value will be 14.56 J, right, but negative. Now that you have value of positive sequence current, you can calculate the actual fault current. And this time as well, the formula will remain same. The value of IA1 into my MVA divided by root 3 kV, and you already are having value of MVA and kV, and you just calculated the value of IA1. So you can find the actual fault current, and it will be 7642 amperes. Now you have to find the value of inductive reactance that must be inserted to control the fault up to 50%, right? You have to insert an inductive reactance that must be inserted to control my fault up to 50%. And you already know what is the value of fault current, right? We uh, we already have the value of IA1, right? And once we already have the value of IA1, the 50% of it you have to acquire. So it will be 50% of this 14.56, so it will be 7.28 per unit values of that will be your IF. Now remember what is the formula for IF. It is given as EA divided by x1 plus x2 plus x0 plus 3xn, and here we have to calculate the value of xn. So what we will do, we will simply make this reactance values subject, and we will simply substitute the values on it. You know the values of x1, x2, x0. You know the value of IF and EA as well. So you will simply substitute all those value in it, and you will make xn is subject. And when you do so, you will find the value of xa will be equals to j into 0.0687 per unit. So in order to find the actual reactance which needed to be added, what you will do, you will multiply this reactance with um, your kV square divided by your MV, because basically you are moving out from per unit to actual value. So when you do so, you will find the value, the actual reactance which you needed to be added will be 0.832 ohms. Now for the last numerical which I wanted to discuss. So here we will start from this one. Okay, I think I actually misplaced them. So we will start from here. So see, what is the question? We have been asked that a 25 MVA 13.2 kV alternator with solidly grounded neutral has subtransient reactance of zero point 0.5 per unit, 0.25 per unit. The negative and zero sequence reactances are 0.35 per unit and 0.1 per unit respectively, and we have to find the fault current when a single line to ground fault occurs at the terminal of an unloaded generator and when LL fault occurs. So initially we will calculate for single line to ground fault, and then we will go for LL current. Now you already know what is the formula for single line to ground current of fault current at single line to ground current, right? It will be same as IA, and IA will be same as 3 times my positive sequence current. So the formula for positive sequence current is equals to EA divided by x1, x2 plus x0. You already know the values of x1, x2, x0 because they have given in the question itself 0.25, 0.35 and 0.1. You already also know the value of EA, which is we are taking normally unit. So 1 and 3 in multiply with it. So the value of IA will be minus 4.28 into J per unit. And to find the actual fault current, to remove this per unit value, what we will do, you will multiply this value with your MVA divided by root 3 kV, and when you do so, you will find the actual fault current is equals to 4680 amperes. Now to find for LL fault, things are much more easier because you just have to add two impedances. right? You just because in LL fault, remember, we don't consider zeroth sequence current, zeroth sequence reactance. So here you will be adding just positive sequence and negative sequence reactances in denominator, and numerator you will be having root 3 into ea, the formula for fault current, which was equals to root 3 ea divided by x1 plus x2. You know the value of ea, you know the value of x1 and x2 as well. So whenever you do the math, whenever you do the summation and division, you will find the value of fault current if is will be is equals to minus j 2.87 per unit. Now to convert this per unit value into actual fault current, you will again multiply this per unit value with your MVA divided by root 3 kV. You already have MVA is equals to 25 given in the question, and kV is equals to 11 kV given in the question as well. So simply substituting these values, we can find the value of actual fault current, which will be equals to 788.2 amperes. So I think we have we saw enough number of numericals. So from now on, I think you will have confidence to go and exam and crack the numericals as well. If you have any doubts related to this numericals, or you want me to explain a little bit in detail about any of the step of these numericals, you can mention that in the comment section below. If you have any feedback related to this channel, this playlist, or any other thing, you can mention that in the comment section as well. So for till next time, goodbye. Thank you very much for listening. I will be seeing you next time with a very new playlist. Till then, take care and goodbye.